It will play automatically.
Okay, good afternoon. Welcome to the afternoon section of PPS and supply chain joint session. This presentation is a kind of a continuation of the morning presentation. It's more focused on a use case related to supply chain traceability in agri-food industry. So my goal is to show you how we are using a reference ontology in a more specialized application, which is tracing food. This project is funded by NIST, and Evan Wallace, who is our NIST collaborator, and Rudy Yoder, he's my grad student and the programmer actually for this project. So again, in agri-food industry in general, traceability is a very critical issue. You need to be able to find the root causes of problems in any type of food products and go all the way back to its sources if there's any issues in the health issues in the product. And there are government rules and regulations that require companies to trace back their products to their root sources. There are a wide range of diverse participants in agri-food supply chain. That's one reason we have some complexity here. And end-to-end traceability requires complete and consistent information. Again, we shouldn't have like dealing with fragmented pieces of information, but we need consistent and harmonized data. So for those reasons, it's not an easy problem to deal with. There's an existing framework, they call it CTKDE by Institute of Food Technologies. So it's based on critical tracking events and key data elements. So during food supply chain, there are some events like transportation, transfer, processing the food from, so those are the events that we need to track because contamination might occur during those stages. So like transport, load, unload, transformation, receive. So they call it CTE. And then within each CTE, there are a bunch of key data elements we care about: date and time, location, description, all IDs, where the material is coming from, all those when, where, what, and who information. So the question is, can we put this framework under an ontological umbrella and kind of model CTKD framework as an ontology? So adopting standards would address some of those issues, but it's very difficult to kind of adopt standards that is accepted universally across food supply chain because of some political and some practical challenges. And I'm sure Jim is aware of those challenges in supply chain, especially in food supply chain. So alternative approaches use ontologies because they are more flexible and more extensible than standards. They don't need to go through those very complicated verification and approval process. So that's why we would like to take an ontological approach. So how ontologies would help here? So standardization and providing a common understanding of the terms in the domain. Data integrity, we have data coming from various sources that they don't interact with each other. So how to integrate data, that's one obvious application of ontology. Semantic mediation and integration, and reasoning for history, exploration, discovery, and construction. Because typically there are a lot of holes in the data. So how to fill the gap, how to connect the dots, and how to add new knowledge to existing knowledge. So that's the current situation. So each of players, farmers, shipping or carriers or factories or distributors, they have their own information or data model and standards. So our data is kind of fragmented, right? But if we use ontologies, hopefully we'll have a connected and coherent data set that we can query, reason over, and understand, and enable end-to-end traceability. So to address that problem, we are using IOF's strategy and procedure. Supply chain reference ontology is used here, and we are extending supply chain reference ontology to create an application ontology. So this traceability ontology is not reference ontology, but it's an extension of supply chain reference ontology. There are multiple use cases. So we picked the use case for which we had data, and that was a use case that we were able to collect some data from. So we call it harvest to on-farm storage. From harvesting the grains to storing in bins. So you would like to be able to go back and trace where these grains are coming from and which field are harvested from, what timestamps are used. So that's the use case. And just tracing back from product to processing plant and to farm itself is not sufficient in terms of granularity. Yeah, yes, it's great to know, okay, this bread is coming from this factory and from this farm. Bread is coming from this factory. Okay.
Just testing. I got message here that somebody couldn't hear us, so I'm just testing that.
Oh, people can hear it now. Hopefully they're okay.
Yeah. I mean, you're okay.
Yeah. So this is. I can frame this picture and put it in my living room. That's like a piece of art. but in reality, that's a farm, and these are that's a field. They call it field. I learned a lot of agricultural term in this project. So they call it field, and these little rectangles are subfields. So in our model, we should be able to address each of these subfields individually. So that's a challenge. And I have another artwork to show you. And this is real data. So when you fly over farms, maybe you have seen these circles. So these are real farms, because I guess the tractors prefer to move around circles, right?
It's because they're probably using pivot irrigation. So they have, and they spray around in a circle.
Yeah, that might be. But these black lines are the GPS location of the combine, apparently. So that's the data is actually coming from Purdue. They did a research. They wanted to do a similar work, but through machine learning. But we are using the same use case, but we want to use the ontologies. But yeah, all these data, all these points are GPS data, which is transmitted like every 2 seconds. The combine sends the GPS data. And so we would like to know exactly these seeds in which location actually in this field based on the data. So we have a lot of data, but how to learn and process and to use it, that is a big issue. So again, we have by now we all know that for ontologies we need competency questions, right? So these are competency questions for this use case, and some of them really get complicated. For example, the first one is in which bin was grain stored for the outbound shipment with ID, whatever. So, or what are the likely sources of suppliers, or what type of critical tracking events take place in the Asheville malting facility. So I try to simplify these questions, but in reality, those queries are much more complicated. Each query might have five or six lines in natural language. So these are the type of questions be able to answer, and these are the relevant terms like event, CTE, transformation, transfer, facility, container. So container is a big factor in this ontology. Load, lot, batch, and so these load, lot, batch, they are used in production plants as well, right? So we should define them such that it's not just for agricultural use cases, that they can be applied to manufacturing use cases as well. So for example, you can see different types of CTEs we care about. It can be maintenance, movement, including transfer, sampling itself. You take a sample of a grain, so that is a critical tracking event we care about. Transport, observation, custody change, ownership change, and there are difficult terms to define. So what is custody? What's ownership? So we have not been able container. So that's kind of counterintuitive. Flexible enough, such as the tabletop can serve as a container for moving stuff from point A to point B. So you can see we have different types of container defined in this ontology. And so TRUs are, so load either can be source load or target load. I'll give you examples of that as I move forward. For example, here is an example of a source container and a target container, and we have a transfer event moving. So the definition is a movement event in which the location of the participating TRU is changed from source container to a target container. So that's the event we care about. The participant in the transfer event, we have the TRU, which is the load itself. We can have the container. We care about the operator or the equipment that were involved. Maybe they were contaminated or they had some issue. So we should be able to track them as well. It's not just enough to, for example, timestamp the transfer event. So because this transfer event occurs on a temporal interval. And that temporal interval has a starting instant and has an ending instant. And that's the pattern we use in IOF for time stamping temporal interval. So each temporal interval has a first instance and the last instant, which is date or time, date time identifier. TRU itself is a collection of material with some shared history for which some agent may have a need to retrieve information. So right now it's treated as a primitive term in the ontology because we don't have all of the terms we need, and the definition is kind of difficult to formalize. So it's very difficult to identify necessary and sufficient condition, but for lot and load, it's easier to define them properly. Load, for example, is an object or object aggregate that bears a load role, and role is used very much in this ontology. And load role is a role that inheres in an object or object aggregate when they are transferred or transported together. So then a portion of corn can play a role, load role, when it is transported together from one container to the other container. And there are examples of containers. They can be like trucks or carts or bins. But again, we are using role such that every object can play the role of a container. So container role is a role inherent in an object or a spatial region when it wholly or partially contains some material entity. And that's the class diagram for container. As you can see, it is an object or object part or fiat object part. The surface of a table is a part of this table, so we can treat that only as a container. And again, we have source container and target container. We should be able to kind of differentiate between those two. And obviously, the location, the geospatial site of the container matters for us, and the tracking event in which the container participates. Field versus field site. So that whole big field is the farm is actually our field, but it can have subfields. Subfield is part of field, which is a piece of land. So piece of land itself is actually a fiat object part, which is part of the planet Earth, right? So we don't have planet Earth in our ontology. That's why, again, that remains to be a primitive. We are not defining necessary and sufficient conditions for that. Well, the whole idea is that if we can really collect all that data about different transfer events and different containers and connect them through timestamp, then instead of querying a complicated knowledge graph, we can visualize it. So especially for domain experts, well, they have no training in a SPARQL, but if you show them, hey, this is the graph, this is your traceability graph. If you want to see what is the source of this load, just trace it back, and there are some forkings happening. But that's a better perspective for just giving them some idea about where are the sources of your loads. So that's why in our validation, we decided to go and try to visualize the knowledge graph, but not the entire knowledge graph, but only a subsection of knowledge graph that kind of shows the flow of material backward and forward. So the research questions was, can we streamline the trace and track process through supply chain data visualization? So in general, data visualization is an active area of research in knowledge graphs, and what aspects of data can be efficiently visualized and how it would benefit domain experts. So we had some UI development, alignment of mapping of the data with the ontology. So we did validation with a simulated data set, and then we did some validation with some real data set. But again, like any other use case, it's very difficult to find real data from farms and plants. That's why our simulated data was much larger, much bigger than the real data. So this is the simulated data. We had like 400 transport events, 400 loads, 4 combines, 5 cars, 3 trucks, and 2 on-farm storage bins were involved. So then we had some software development because the data is in CSV format. How to map data from CSV to RDF graph. There were some existing tools for mapping. We realized none of those existing tools for mapping really meet our purpose. That's why we created our own customized software for mapping the data to our ontology. So these are the key data elements we care about. And so that's the CSV mapping. So it's mapped to a CSV file, and we can say, okay, this column, so for example, column B is a right map for target container type, or column C is the right map for event end type. So after doing this mapping, and it should be done manually only once. Once you do the mapping manually, and you can see some examples of data for each of these IDs. So first select CSV file, then do header mapping, then submit. Then when by pressing the submit button, what happens? We'll get actually the RDF triple. So this mapping is happening behind the scene. The user does not need to be aware of what's going on because there are lots of complexities in ontologies, and so we don't want to even use the term ontology when we talk to some experts in this area. But this is happening behind the scene. What they do, they simply select the right column and map it to what we need. So it's kind of closer look at the mapping. It says that, okay, transfer event tab, column I, the start time is mapped to the text value for a temporal instant, for example. So these are done behind the scene. And then next step is graph generation. So we need to pick what's the starting zone or subfield we care about. And then, we already generated the graph. We just import the RDF graph here. And then select the field node zone as the root node. And then, so this field is one of those rectangles in the first graph I showed you. And then step 3, generate the traceability graph for the selected zone. So this is the graph generated before sorting. So this is a sub-tree under the larger knowledge graph, but obviously this graph is not very useful. But if we arrange it chronologically, then you can start making sense that, okay, this field, there are 3 transfer events, or each transfer event is a combined harvesting seeds. So these are the combines, and then combines are moving material through another transfer event to a cart. Then there is a forking happening. This cart is through 2 transfer events, moving material to truck 1 and truck 2. And then this green box is a transport. The truck moves the material from point A to point B and basically stores it somewhere. So in that way, we can move forward, trace forward, and track back, and kind of get a feeling of what's happening and where each load is coming from. And we can drill down and focus on, for example, one load and get information about identifier, volumes, participants, and timestamps. Or here we can zoom on a load, this strike load, what's the volume, what are the participants. So in that way, really, the domain expert doesn't need to worry about querying that complicated graph. They just select a node they care about, they get more information about that node, right? And this mindset or this framework can be applied to any type of supply chain. It's not just for agri-food. Yeah, and then you can analyze the event. So I'll not go into too much detail there. So again, on visualization, we started using Stardog. I don't know if anyone in the room has experience with the Stardog. Yeah, so I don't know how was your experience, but after some like try and error, we were able to generate some useful graph out of that, but it's still, as you can see, there are some still alphanumeric BFO things in there that part of it is readable. For example, a transfer event is a type of movement event, is also a type of transfer event, and it occurs. And field 1 is where this transfer event occurs at, and basically some of it is readable, but some of it is not. But still, we are happy to be able to get something useful out of Stardog. Stardog has 3 sub components: a Stardog Explorer, a Stardog Designer, and a Stardog Studio. This is part of a Stardog Explorer. And again, so that's the load is a type of object aggregate, is also type of a portion of V, and so has portion. So this load has several sub portions that you can see through these pie charts. So again, that's kind of useful. You can make sense of data through this type of visualization. So next step, we would like to cross-validate with different type of data set. We received recently a JSON data set from through a gateway, in fact. So that would be interesting to see if we switch the data from CSV file to JSON, how the system changes. We need to work on user interfaces because it's still there are some type of queries that can be run, but it should be better if we can have some UIs for that. And then expanding the list of available key data elements and improving graph visualization feature. And now we have moved to new use cases, or from elevator to processor and tray harvest back to seed. In fact, we want to go back all the way to the seed manufacturer, where the seed of this bread is coming from, not where the grain is coming from. So it's even one level deeper in the supply chain. All right, I guess I'll start here. I'm kind of on time.
So can you go back one slide? So going back to the seed, are you going back even where in seed? Would it include seed treatment? Or just, okay.
Yeah, seed treatment is also.
That's a mess as well.
Yeah, so I was learned that as you treat the seed, the color of the seed changes as well.
Yeah, no one cares about the color.
Yeah, but it's kind of, yeah, we would hope to go there, but because we don't have data from that stage, maybe we'll avoid that for now. For now, we'll just from planting all the way forward.
Right.
Yeah, so that's the scope. But if we can get some data set from before that, that would be really interesting.
Yeah. One comment. I mean, you began your presentation saying that there are political and practical issues with, improving supply chain. I think it's primarily business. Acquiring data for the ag industry in the U.S. is incredibly difficult. So some of the I led a project 2 years ago on applying blockchain for seed input supply chain and crop protection products.
Okay.
And it failed, and we had BASF involved and Bayer Crop Science. The reason it failed is nobody wants to talk about what happens in the process and what the behaviors in the industry really are and what motivates the behaviors. So this is really interesting. But I think with all this ontology stuff, it seems like we tend to do this work with the assumption that all the people that should benefit are, being honest and straightforward and
Yeah,
about what
that's
they're doing.
not the right assumption in all situations, but at least it gives us some perspective on what are the interoperability
Right.
issues.
Yeah, and then another question with respect to the, you indicated it goes from field to combine to grain cart to truck to on-farm storage.
Yeah.
Were you also looking at grain elevator and then traceability of grain through the grain elevator?
Yeah, in fact, that is our new use case. So from
So
October,
that'll be next.
yeah, that will be next, and that will be fun because there are more processes involved and more complicated use case.
Right.
Yeah.
Because it all gets commingled.
Yeah, exactly. That's another story.
I have two questions. One is ontological, second is use case focus. So if I am not mistaken, your event is not subclass of process. Is that correct?
Yeah, so it's event is from IUF event. So IUF event is a subclass of process, right? So,
I think I thought your graph is not. I may be wrong.
Yeah.
Yeah, it's not.
oh, is it subclass of occurrence, not
Yeah,
process?
because it can be processed.
Oh, that's right. It can be process boundary as well because it can be either a process or process boundary. Yeah, that's
No, but okay.
that's right.
Second question. So, in your use case, do you need to trace tracing events? Do you need to trace duration of processes or events? For example, if yogurt stays outside of refrigerator for long, it's going to be stale, or many other food items.
Yeah.
So, do you trace that? Do you intend to trace that?
So each event has a duration, right? We need to know what's the start time and the end time of the event.
So why is that different from process then?
Well, because there are some events are kind of instantaneous, right?
So it means start and end at same time instant?
Well, in fact, in our case, in this use case, we don't have any instantaneous situation, but because we are using IUF events, then we have to put it under occurrence. But in reality, all of our events are type of processes. They have duration. In our use case, we didn't have any instantaneous process.
Thanks.
So I have one question.
Can you speak up so for microphone?
Yeah.
Just speak louder, not stand up.
So I have one question about how you are differentiating between the container and the package, because like in terminology, we from supply chain perspective, we use equipment as a superclass for container and package and pallet. So package, pallet, container, they all come into equipment class.
Yeah, I see your point. And you see, there is a container artifact here. So when we say artifact, it means that containing is a design function of that object. So a box is designed for holding things. That's why we put box or package under a container artifact.
Okay.
But here we wanted to keep the scope kind of broader. So here this container is actually realized through a role, container role. That's why everything basically can become a container. Technically, like whatever entity you can imagine, object actually. So whatever object that can take container role becomes a container, like a subfield or here the grain bin is a real container, but we decided to take a little bit more high-level approach than looking at function of that object.
Okay.
Instead, we are looking at the role of the object.
And NIST traceability tool is open source or?
Well, yes, technically it is. We have not uploaded it on GitHub, so maybe that's something I need to do when, yes, it is. I need to check with NIST, but most probably we can just, it's a jar file, it's a Java tool.
Okay.
We can upload it on GitHub, and if we can provide sample data sets such that we can hack it and break it and play with it.
And like this seems like it has a lot of potential to solve the business problem in supply chain. So are you going to extend this to transport side? Like
Yeah, intentionally, when we designed the tool, we decided to take more generic approach and assume that most probably the same framework can be applicable to other applications, transport, logistics, not just agri-food, because this is really the more complicated situation. If you go to the logistic use cases, they are much simpler than this one. So if we can address that question, that problem, we can also address the other one. Yeah, but I agree with you.
Because like food wastage is one of the main problem in container shipping industry.
For what?
Food wastage,
Okay.
because of like the data integration and sharing is not smooth,
Oh yeah, yeah.
and so that's why like there are like some legal procedure going on between two countries, the stakeholders in two countries,
Oh, of course.
and if there is one mistake, then the other side, they are not able to receive the goods.
Yeah,
Port
yeah,
authority
yeah.
will not release.
Yeah, there are
So-
a whole lot of like legal and regulation issues here involved. Yeah. Had a question?
Yeah, very quick one. I saw in one of the slides you mentioned the rearrangement of the RDF graph.
Yeah.
So you're using any specific tool, or it's like part of the?
Yeah. So I need to ask my student Reed, because yes, he's apparently using something to convert this mess to something more readable. I can get back to you on that.
This more readable is better, right?
But these are known graph processing algorithms in computer science.
Yeah. Okay. There you go.
Where you just reorganize, look for cycles. So
Yeah.
it's
Yeah, basically.
Yeah.
But the software or the tool has to have function to determine the location, etc. Right?
no, that's only display. That's only display. It's just visually display. And you can
Because
parameterize that.
Yeah. Yeah.
I thought the contour graph also has an option to show it as a tree,
Yeah, but
I guess-
but it doesn't give you the option of selecting a sub part of the graph the way you want. So it's kind of more customized view than on the graph.
And one small experience, because you mentioned in one of your slides that it's unreadable the names of the relationships. Because I had the same problem.
All those BFO things, yeah.
Yes, because I encountered the same problem, but I was using Neo4j. I saw it is the problem of during the importing, we need to do some configuration to map the RDF, because in the RDF original RDF ontological graph, we have the different attributes like name, label, and URI.
Yeah.
We need to configure which one to show here. I'm not sure if it's the same as in with the so it's
Start
some
like
experience.
I guess it only shows the qualified name or the local name.
Exactly. So
Yeah, that's the problem.
There's this option at least for Neo4j that you can configure which one to show.
Okay,
Yes.
that's good to know.
Yeah, but I'm not sure if it's the same for Mastodon.
Yeah. Most probably, a startup does not have that feature.
The biggest problem is actually if you try like type Sparkle, like trying to do a live demo and type Sparkle, and then you have to put those BFO relations in as you're building your Sparkle
Yeah,
course.
that's a nightmare.
I struggle a lot to get that theory.
Those are 55 and 54.
Emilio, you had a question?
Yes, thank you for the talk. I mean, can you comment a little bit more on the data mapping that you show us in the slides? Because I mean, I didn't understand what you map there. I mean, do you state equivalences? Because then in the graph that you have next, it seems that you state different types of relationship in the. So what are the things that you?
Yeah. So for example, we are looking for start time of an event, and we know that it is one of the columns in our CSV table. So then we say, okay, go and find end time. So start time maps to event start time and end time. So this is.
So you make the mapping between your CSS file to the ontology.
To the ontology.
And then you populate the ontology automatically.
Yes, that's the thing. So this mapping is done manually once, and this mapping is saved, and in future, as long as we are importing the same data structure, we can reuse the same mapping. Yeah, that's.
And how are your data specified in CSS file or your also other types of?
In this situation, we had CSV file, but now we have received JSON file. We are just working. I mean, there's a fundamental difference between them, but yeah. So we need to reformat the tool such that it can also accommodate JSON. Right now, it just works with CSV.
We don't have relational databases.
No, we are not using relational. So in the background is OWL API doing everything. Yeah.
Okay, thank you.
Yeah, sure.
I have one question about adoption of the solution, because you have in your chain of supply and everything, you have actors of different sizes with different financial power or manpower or resources to adopt these solutions. What are your experiences? Do you manage to convince the smaller ones who maybe have only 2 farmers working and tell them to implement a new system which they don't understand?
Yeah, obviously that solution that shouldn't work, right? So because smaller farms, they are not they don't have the sophisticated IT background to take care of this type of activities. That's why it starts from upstream, from the OEMs maybe. Is that correct, Jim? Can you just?
We don't have time. If you want to explore it, I can talk for hours about it. So, but yeah, I mean, just quickly, in the United States, the agricultural equipment is generating petabytes of data for kind of big fields, even over the course of the season. So there's challenges of getting it from the equipment to a farm management system, getting it from a farm management system advisors to do analysis and provide feedback. Even in these examples, I mean, you'll have multiple streams. So, you show data here, you'll have data from the combine, and in a transfer event, the combine's generating data saying I'm pushing corn to this grain cart. Meanwhile, the grain cart's generating data. So now you have 2 data streams related to the same event. So it is very complicated. Farmers in the United States and pretty much all over the world are really, really frustrated because they pay for all this sophisticated equipment and they say, I buy a red tractor and I hook it up to a green implement and they're not talking properly and I have all this data, you promised to do this and that, and it's, how do I get the benefits you promised? So,
That's nice.
Okay.
but this sort of work is really interesting.
Yeah, it's just to showcase, explore the possibilities. But yeah, in terms of implementation, that's a whole different story. Do we need to check if you have any online questions? We don't have good. All right.
I have one follow-up question. Like you said, on the background there is API. You are making calls to API to map the data to the ontology. So is it possible to send the data directly through to map the ontology through API?
Not in this implementation, but that's an interesting direction to go. Yeah. So I totally agree. That makes a lot of sense.
We have something which goes into this direction in the OntoTrans project, where we try to do some kind of mappings between data sources and OntoKB framework, which we try to implement. And for some types, of course, we cannot just map any data. So for some it will work, for some it won't. But we actually try to have exactly this. We have some prototypes where you can call some APIs with mapping.
Interesting. Yeah. So we have not done that here.
I think we should move on. because-
Yeah, I know. Yeah. So okay.
Who's next?
Thank you.
Okay.
Who's next?
So I'm okay.
There.
Next is Xiaochen Zheng, ontology-based engineering system to support aircraft assembly process design. So I thought we would give him 30 minutes, but I think he wastes some time. So go back to 20 minutes so that we have enough time to talk about a panel on capability. Is that okay, Xiao?
Yes,
20
and
minutes.
we can be quicker because some of the content have been presented this morning and some of the
Okay.
audience are already there, so we can speed up on that part if necessary. you wanna start?
Yes.
Yeah.
So hello. So this is the last presentation of a series of presentations about the subject. So yeah. So regarding this European project that we have made in collaboration with EPFL and Fraunhofer, where we have made a trade space framework in order to have a support to build different assembly process design options, and that the architects can trade with these different design options. So right now I will give an overview in a nutshell if you haven't heard it before, because we have made a little presentation before. And then so explain what was the assembly process that we were dealing with, okay? So that then we can go to the development of the application ontology of this assembly process, and you will see how it was constructed and what we did out of this ontology in this framework. Okay. So yes, in this European project, we had a pilot in which we were aiming to use MBSE and a collaborative design process between the aircraft and the industrial system design. Mainly focusing on three aspects. So knowledge management, interoperability of the system, and decision making for the manufacturing engineers that participate in this design process. So the use case is the aircraft fuselage orbital joint process. I will explain what that is. So it's one of the key processes that we do in our assembly lines of our aircraft, all of our aircraft. And we have a prototype that has been demonstrated and tested with these final users of how they can use it to design this orbital joint process. Okay. So, so this is the aircraft before you fly here. So these are the two sections of the aircraft. So this is the orbital, so what we call the orbital joint process. Okay, so it's an orbit. So you can think like the fuselage. So there's two parts of the fuselage, and you have to put them together. Okay. So the process consists of first, so you put them into place. You have some measurements of the two parts to see that they will fit. So you check that it meet the tolerance specifications, so the product requirements that they have set. If they do, you have a joining process first, so one goes into the other one, and you check if you need some shimming to be done on the interface. And you need to ensure that all the stringers that you see here are matching as well, because you need to join the stringers and the orbital joint process, right? So once this is matched, we will have different technologies that we can use for the junction. So like riveting, shield welding, etc. So in a combination of them. And we have different resources that can apply these technologies. Okay, so we have options like pure manual of operations, or we have a flexible robot that plugs into the fuselage. It can drill and put the rivets and do the riveting process by itself, or with a KUKA robot that holds just the end effector and etc. So we have very different options for different technologies. And you see we have accessibility constraints because here this is the floor, so your luggage normally goes inside here. And so here, all of these areas are very complex to be accessible for automatic systems. So they need to be more manual, okay? And here we have like the windows, and you need to avoid these windows while you're doing the operation process. So you need to consider those constraints, okay? So this is what we give as input for the application ontology, which I think, right? So before that, I'm going to explain the trade space framework. So in the trade space framework, we had two different roles. So an engineer that was defining requirements. So requirement for the manufacturing system. For example, how many aircraft I want to build. I want to build 150 per year. That's an industrial requirement. And we need to find an assembly process that can be suited to manufacture 150 aircraft per year. Okay? So with that, we have different architecture options. So the assembly sequence options, okay? And we run some simulations in order to check that with discrete event simulations, for example, to check that we are able to do that. And then we trade between the results, okay? So that was supported in the backend by the system integration block, where we have the application ontology that will be explained. that here it was controlling the data flow. And also, using historical records, we understood how the process was designed or existing currently, and proposing different architecture options already to the architect so that he can use that as a starting point for his design. Toolchain, very quick. So the toolchain that was supported by the connectivity, the data flow connectivity. We had an open source tool that is called OnRack to manage the requirement. There was a middleware connected to the system integration layer. We had Metagraph used for the architecture models, and SimFi and visual components for the different simulations, so discrete event simulations and 3D simulations that we're supporting. And the system integration, we use Neo4j for this demonstration, and a cloud server to publish an API so that the middleware can call these APIs. And I think that's it. So we can jump into the application approach.
Yeah. Maybe some of you already heard this part already. Basically, we are using the IOF core as the middle-level ontology to as the backbone to develop our application ontology. So during this, this pilot, we have three main parts regarding the assembly process itself. We call it domain knowledge. That is the real assembly process of the resources or the human resource or the tools or the parts components. And then we have the requirement ontology is define the classes and individuals to describe the industrial requirements, mainly connected to the OntoRack tool. And then we have the geographic ontology. This is the MBSE part we explained this morning. It's related to how to translate the domain knowledge to the MBSE knowledge. Basically, it's like a transform from because we capture the knowledge from the domain experts and documented the historical data. And when we want to present this knowledge to the architects, the end users, they cannot read the ontology. They are familiar with the models, and the tools they use is the MBSE tools, for example. And we need to have these three parts together, and then we can translate to different format of models. Here's the general structure, and maybe similar to many other application ontology that follow the IOF core structure. Basically, but here I can see we use the previous version of the IOF core, the draft version, and then of course we know that the IOF core refers to BFO, and between the IOF core and the application ontology, we have another layer called quality domain ontology. This is only because we are developing not only for this pilot, we are also working with other pilots. So we basically developed we can call it subdomain or domain level ontology. Basically, it's below the IOF core and defines some commonly used terms in quality related manufacturing processes. And here we use the model called RMPFQ. Is the most important factors need to be considered during the quality management. And then based on that, we started to define more specific use case specifically the terms. As just mentioned, we have like two main sources for the domain ontology. Domain knowledge ontology, because it's quite confusing. The main part is the documented knowledge. Basically, is the historical process specifications. They are used in the world. They are used in previous similar models of the aircraft, which we consider that some part of it can be reused for the newer models. That is the main knowledge source. Then after that, we need to interact with the domain experts, of course, because we need to make sure the knowledge of the terms we defined or extracted usable and applicable to the industry. That had to be verified by the experts. So after several rounds, we have like a usable version of the ontology, but it's always like updating. Then another important step, I mean, we have the ontology there, we use the protege or web protege. And then next very important stage is to create a graph, a knowledge graph, or graph database, if you want to call it. As I just mentioned, we use the Neo4j, and we import the developed ontology in a Turtle or whatever. The Neo4j, it supports several formats, okay? And then we import, then we create this, we transform the ontology to a graph, a knowledge graph, you can call it. And another point is we can actually do more in graph database than in purely ontology, because we can define the properties for relationships. In ontology, we define the relationships between two objects, this kind of property. But in graph database like Neo4j, the relationships are considered as object as well. So we can define properties. For example, when we are saying that this process needs a robot, how many robots and for how long time and what is the cost? It's kind of difficult to manage in pure ontology, but it's easier in graph database like this one. So basically, here's it looks like, and we define this the knowledge captured in ontology is about the process and some constraints and some essential operations, we call it. And there are also some options, as Rebecca just mentioned. For the same process, we can do it with a robot, do it manually, or we can, if we have the whole orbital, we can separate up and lower, or left quarter or right quarter. We can do it sequentially, considering the constraints of the resource, or we can do it in parallel. So many different combinations. That will result in huge number of options for the future assembly process. So to help or to support the designers consider all possible scenarios, we created this kind of software or this algorithm, basically, because the graph database that I mentioned, it supports integration with the different programming language that makes it very flexible. To integrate the querying languages, here the Cypher is provided by Neo4j. Integrate this querying language into the Python script, so it can run automatically. And then we here we assume, and I mentioned it's not exactly, because as I just mentioned before, we have some special points need to be treated separately. Here we consider them as whole. Then we split the whole orbital join process into upper and lower. Then each half can be further split. So here's our three levels of the process. Basically, we decompose the whole orbital joining process into 4 segments. That's where we play the sequencing issue. Because each quarter, normally, you cannot decompose again, because you cannot do sequentially and parallel. I mean, you cannot further decompose, basically. Then we have these constraints or rules defined, and then I apply them in this algorithm. We can step by step create one template. Basically, we create some essential operations for the first level one, then create some essential one for the second level one. Then we have all of them. Each time when it's encountered one optional operation, there will be a fork created. So it's like a nested loop in the algorithm. So basically, in the end, we will have multiple solutions created automatically. They are like basically something like created based on the knowledge we captured before. Here's it looks like in the graph database. It's just for sure how it looks like in the database. After we have this solution generated, we need to verify which one is better, which one is not, and which one can be satisfy the predefined industrial requirements. And before this, we have a BSE part. It's like how to transform the solutions to different models so that the architects can reconfigure and optimize. There's pre-selection there. Then imagine we already after that stage, okay? After that, the selected solutions will be saved back to the graph database. Then we can, the 2D 3D simulation module started to work. They extract the selected solutions to trigger the 2D simulation, 2D and 3D simulation. Here is some examples of the 2D simulation. Basically, is the calculate some key performance indicators based on the predefined requirements, and then we can show the results in web-based service. This is basically the workflow of the 2D simulation. Here's examples of the requirements defined, and here are the generated solutions and extract some key values from it. Then we can calculate some the indicator, the value of the indicators. Then we can verify if it's larger or smaller, or it's satisfied or not. And this is the workflow of 3D simulation. This part is supported by Visual Component, as mentioned. We have this 3D software can import OWL file directly, map them to the 3D elements in the software so that they can trigger the 3D simulation. So, but in the end, as we did a quick overview of the workflow from the architect's perspective. Basically, this is what the end user sees, because as we mentioned, we cannot show the ontology directly to the end user. So basically, here's the overall process. Here, here is using the OntoRec software to import the industrial requirements. Sometimes it's in some Office, Excel, or Word files. With the software, we can import that one into this system and transfer into this format. Then these requirements are integrated into the graph database. During this process, of course, the actors can always redefine or change the configurations of the requirement. Then, as I mentioned, this is the key part to generate all the possible alternatives of the assembly process. After that, it will go to the BSE part. This is not introduced here, but it's a separate software where they can import the generated processes, and here we can transform it into different models, which are more familiar to the architects, but they are using them already to design the processes. Okay? And of course, they can reconfigure or optimize the automatically generated solutions and then send back to the graph database. Now here you are seeing is the 2D simulation results. Basically, there are a list of KPIs. You can choose which one to check and to compare. There's different ways to show the result. And then we will know, for example, here we generate 18 scenarios, and we will know which one is which one can satisfy the requirement, which one not, and we can also order them based on some KPI. And then 3D simulation, they import the OWL file and trigger the 3D simulation. And 3D simulation, it supports both on computer presentation, and also it supports VR. You can wear this goggle and you can check in different steps. It's more interactive. Yeah, I think that's it. Open to questions and discussions. Thank you. I'm not sure if the video is still playing downstairs. They are in the hall. If there's a broader introduction to the pilot, because here we're focusing on the algorithm. In the morning, we focus on the MBSE part. If you put them together, we have a more complete picture.
Question, are you using the property graph instead of RDF graph?
No, we are using RDF.
Okay.
But after importing the ontology was imported in turtle format. Of course, we can also import as OWL or other format. After the ontology was imported to the graph database in Neo4j, we did some modification because we didn't define the the attributes for the properties. Because in the ontology, for example, we defined this drilling operation. It requires resource. Requires resource is kind of property. Then the range is power drilling machine. But when we define the requires resource as a property, it's not that easy to define attributes for this property in the ontology. Because we, for example, we want to know how many drilling machines does it need and how long time does it need. This is, you can manage it in a bypass way, but it's not manageable easily. So, but once we import that ontology into the graph database, then this property is treated as an independent object. Then there's a possibility to add these attributes to this property. And we can add cost, etc. Yeah.
So I take it, since you're using Neo4j, you weren't doing any reasoning?
I won't call it a reasoning. I mean, it's like in between. It's not like we do reasoning in the ontology. In the ontology, we define the rules. You generate some new entities, but I would rather call it just a generative algorithm, because what we did is actually define the rules. I asked them to run the query, tell me what the orbital joining process looks like in the ontology, and what are the essential operations for this orbital joining process. If there's an essential operation, please create this create a new individual for this class. And if it's an optional operation, then create 2 for me for each of the options, or 2 or 3 for each of the options. Then you have, in the end, you have forks. In the end, you have the generated solutions. It's not well, some people can call it reasoning, but it's not like a reasoning we did in ontology.
Yeah, so you can infer classes, class relations.
Yeah, it's basically
axiomatic.
Yeah, it's basically automatically control how to generate individuals from the class. Yeah.
So are you creating any duplicates when you do this? If you come from different direction, is there any duplicates in your data graph?
Duplicate, you mean the generated process, or when we are storing back to the graph?
Processes. I mean, you started forking, so if there are alternatives, you fork at any level. So if you go different paths, duplicates. How do you manage that?
We can avoid that when we're designing the algorithm. But here, to simplify the process, because Rebecca showing the picture, we have different, the upper and lower is different. We should treat them differently, but in this case, we treat them the same, so that we can write the algorithm shorter. But in reality, if you want to treat them differently, we just adjust the.
Are you missing any performance if you do that?
In this case, it's easier to handle, so we don't have that much.
That's what I mean. Easier to handle, but you're sacrificing potentially better performance. If you consider all the alternatives.
Yes, that's the origin and the raw database we have. The options are limited. So in the generated processes, it considered all the possibilities. But the only cases, the only issues in this pilot, the available possibilities is less than the real industrial system, because we are using a dummy data set. It's not a complete.
Two questions about simulation. So
yes.
What kind of randomness do you introduce into discrete event simulation?
This one was not done by me, but There's no.
You're a presenter, sorry.
Yeah. I'm trying to recall for the
Is it a simulation in that sense? I thought it's more like
no.
simulation to find whether.
There are two processes. Yeah, there are two processes. For the calculation itself, there's no distribution, but there are some parameters that need to be considered. For example, the fault rate, the downtime rate, etc. We consider that. I mean, we talked about that. In the end, which number we find actually not 100%. Sorry.
Even that downtime rate is also randomness. So do
Yes.
you run this given simulation with random probabilities, or you're just doing averages?
Yes, so we consider them. So in fact, so here what we pushed is first the topology, so the assembly process sequence, and then there's a configuration step where the architect defined the design space, and he designed this randomness on these specific design parameters, saying, okay, I want to run my simulation so to check the performance of these assembly process in these conditions. So it was.
Yeah, but the assumption is that if it's manual work, it's going to be variability higher than if it's robot work.
Yeah.
Yes.
But that was verified then on the simulation loop. So we after the model was built, for the sequence, we predefined the design space.
And last question, so in your animation, you showed these operators moving. How do you visualize if you use robots for these operations? Did you visualize robots on robot operation or not?
Yes, I think at least for this already have the KUKA robot because they have
Is it the actual robot control algorithm, or is just visualization that something is moving? I think some of these usually 3D animations, if you use operators, they're just basically showing they're moving, not really doing anything, just basically making some dynamic picture.
Yeah, I think here all the elements in the 3D software are predefined by the software company.
Yeah, okay.
Yeah, then they need to get the attributes and data from for example, if the robot you're mentioning, they need to get all the performance of the speed or control parameters.
That's why I'm asking. So is that simulation, 3D simulation, is running robot control?
Yes.
Or it's just for visualization?
As far as I know, they have that one for KUKA, but I think that's the only one they have. That's why we are not showing that, because in Airbus we're using a different. So
Okay.
They had a library of predefined behaviors that we were using here for the permissions.
Yeah.
It's predefined, maybe not exactly what is happening.
Yeah,
I understand. That's
it's like a library. You can always add new ones.
And just one,
Oh, yeah, I just want to make a comment on how you.
And I think online people don't see presentation, so I don't know. There is Arco, somebody.
Arco, there's a problem with the connection.
It seems that online people didn't see presentation.
Didn't see
here
presentation
presenting
or only the question part.
I don't see any chat. Let's share again.
That's your question.
Okay, so I'm just thinking, the way you handle the quality of the view. Perhaps you want to make it more appropriate or more in line with the VFO. I think you need to create like a object aggregate for the view, like a view group on your object aggregate. And then you can specify the quality, right? That will follow the VFO.
Actually, that was good. You prompted me. I had another question. So, in which way IOF core helped you? I think this is relevant, important for this group.
Yes, exactly.
You use the very old version of the.
Yes, because we started this project like more than 30 years ago. So yeah.
Anyway, but I mean,
So, yeah.
I think question is still relevant.
Yeah, I mean, for PFO, at least for me, it's like a very good starting point. We already have the struct there. So what we can do is, because it's like both top down and bottom way, we already have all these terms defined in the document. We just need to adjust to align them with the IOF core. And if it can be mapped directly to the IOF core, it will be perfect. If not, we define a new subclass or like a parallel class to be of course, and makes the development of the ontology much faster. And of course, there's other advantages like you use up-level ontology, it makes it easier to extend in future. So
Okay, thank you.
thank
I
you.
mean, there's more questions, but I don't want to take time because
Yeah, thanks.
we need to go with next
Yeah, thanks.
presentation. Thank you.
Thank you.
Very good. Next is panel that Tarko is supposed to be